Hey guys, welcome back for our second geometry lesson. Today we are talking about the segment addition postulate. So if you remember from yesterday, a line segment is a part of a line with two endpoints. So the segment addition postulate is going to deal with how we can measure that segment. Two things you need to know. First off, what is a postulate? A postulate is a rule that is accepted without proof. We don't have to explain anything, we just know that this works. Theorem, though, is a rule that is proven. So at some time, someone proved that that rule does work. One thing I would like for you to do is get out a ruler and measure the segments to the nearest tenth of a centimeter. And this isn't something that I can do easily with you on the smartboard, but I will go over this in class with you. So if you will take a second right now, pause this video and measure those segments on your notes, please. All right, I will tell you that if you are using centimeters, you should have gotten 4.2 centimeters for this first one and 2.7 centimeters for this second one. So we'll go over those in class if we need to. Okay, so the ruler postulate then says that the points on a line can be matched one-to-one with real numbers. The real number that corresponds to a point is the coordinate. Of the point. So the number that corresponds is the coordinate. We've heard that word coordinate hopefully when we're talking graphing. So this time we're just talking about the x coordinates, essentially, where that lies, kind of its address of where it lies. The distance between points A and B is written as AB, is the absolute value of the difference of the coordinates of A and B. So all that means is, let's give this a number. So if x is at 3, or if x1 is at 3 and x2 is at 7, the difference would be 7 minus 3, which is 4. Or you could say 3 minus 7, but when we're talking distance, we don't ever say something is a negative number of miles. So that's why we have to put that absolute value. Absolute value just tells you to take the positive of that number. So the absolute value of 3 minus 7 then is also 4. One other thing that I need you to take from this is this notation right here, this AB. So when we wrote our segments, here's segment AB. I read that as segment AB. If I write AB without that bar on top, I want to know the length of that segment. That's something that you need to know, that notation. With the bar, we're talking about the segment. Without the bar, we're talking about a length, a numerical value there. Okay, so let's talk about the segment addition postulate. First off, I want you to think about if you were taking a trip. Let's say you were going from Kansas City to St. Louis. And I tell you that it is 150 miles to Columbia, Missouri. So here's Casey. Here's Columbia. It's 150 miles to go from here to here. And then it's another 150 miles to go from Columbia to St. Louis. Could you tell me the total number of miles of your trip? Hopefully you would say that it is 300 miles total. So all you did there was take the 150 miles from Kansas City to Columbia, and then 150 miles from Columbia to St. Louis, and you added those together. That's what this segment addition postulate says. It says that if B is a point between A and C, so Columbia is a place between Kansas City and St. Louis, then we add those two segments together. So we add segment AB. So AB, BC, we add those together to get that total length of AC. Same thing is true if we say if AB plus BC equals AC, then we know that B is between points A and C. So it asks us to find XZ. Notice that bar is not on top, so we're talking a length. So from X to Y is 7, from Y to Z is 12. All we need to do there is add those together, so 7 plus 12 gives us 19. So XZ equals 19. Okay, then it wants us to find RS. So here I see that QR is 9, but then it looks like QS is 22. That whole distance is 22, and we want to find R to S. So we're working backwards here. Then if we know that whole distance is 22, we're going to take away the part that's 9 to get 13. So RS then is 13. You could work that backwards to check it. If we add 9 plus 13, we would get 22. This next example, we're just throwing in some variables here. So it says to find the length of JK. So we're going to have to do some work at the end to get this length here. But for now, we know that we can use our segment addition postulate and say the piece, JK, plus the other piece, KL, equals the whole length of the segment. Then we can combine like terms. So 2x and 4x gives us 6x. We bring down our plus 3 equals 33. We're going to subtract 3 from both sides. So 6x equals 30. And divide by 6. So x equals 5. We're not done here though because it didn't ask us for x. It asked us for the length of JK. So JK is 2x, or 2 times 5, which is 10. So JK is 10. Here's more notation pieces here. So congruent segments. That word congruent just means things that have the same length. So, and congruent segments are line segments that have the same length. And this is a very subtle difference, and we'll talk about this more in class. We'll talk about this a lot this year. So when we write it as AB equals CD with no bars, we're talking about numerical values. The numbers are the same. So AB is equal to CD. However, when we add the squiggle to the top, so congruent has the squiggle on top of the equal sign, and we say AB is congruent to CD, we also put the bar on top there. We're not actually talking numerical values, but we're saying they are the same length. I call this the hat rule because you'll notice that everybody gets something on top, whereas nobody's wearing a hat in this one. So AB equals CD. So that may be a way to help you remember when to put the bar, when not to. Another thing that we can say is something is not congruent to, and if you want to say something is not congruent, you just put a slash through that congruent symbol. Okay, the last piece here, we're going to graph these points, and then we're going to decide are X, Y, and W, Z congruent. So Just a refresher on graphing. When you graph, you start at the origin, and then you move left or right, and then you move up or down. So for point X, we're going to move left 2 and down 5. And I'm going to label it X. For point Y, I'm going to move left 2 and then up 3. And I'm going to label it Y. For W, I'm going to move left 4 and up 3. And I'll label it W. And for Z, I'm going to move right 4 and up 3. And I'm going to change colors here for W and Z and make those blue, just so we can see it a little better. So I'm going to connect X and Y, again, use your straight edge. And then I'll connect W and Z in blue. Now we want to know if they are congruent. So the first thing we're going to look at, the easiest thing to look at, is do they have the same length? So I want to know the length of XY, so I don't put the bar on top. So I count the boxes. So XY is 1, 2, 3, 4, 5, 6, 7, 8. And then I'm going to count the boxes for WZ. And it's 1, 2, 3, 4, 5, 6, 7, 8. They both have the same length, so then we can say XY is congruent to WZ. Now right now I've written XY equals WZ. Their lengths are the same. So remember, we're going to put the hats on top of everybody to show they are congruent. So I put the bars for the segments, and then I put the squiggle with the equal sign. All right, so we are going to talk a little bit more about this tomorrow. If you have any questions, feel free to come in and see me. Have a great night.